Welcome to Learn with us. This is the sixth lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you studied about diodes, types of diodes. In your previous lecture, you also understood what is an ideal diode and what are the terminal characteristics of an ideal and real diodes. What are the learning objectives of this lecture? In this lecture, you will understand current equation of diode and you will also understand modeling of diode in forward characteristics, in which you will study about exponential model. First, we will look at the diode equation in forward bias region. This is the equation of diode in forward bias region, where I is current in forward region, Is is saturation or scale current, V is applied voltage, Vt is thermal voltage, and the constant n has a value between 1 and 2, which depends on physical parameters of device. We take this n 1 for diodes and we take this n 2 for transistors. In general, we shall assume n is equals to 1 unless otherwise specified. The value of this saturation current is a function of temperature. For every 5-degree rise in temperature, the value of this saturation current is doubled. Now, look at this thermal voltage. This thermal voltage is given by the equation kT upon Q, where this K is Boltzmann's constant and the value of this constant is 1.38 into 10 raised to the power minus 23. Here this T is absolute temperature, which is in kelvins. This Q is current and its value is 1.6 into 10 raised to the power minus 19 coulombs. Now at room temperature, that is 20 degrees centigrade, when we put this value of Boltzmann constant and this value of current in this equation, we get Vt is equals to 25 millivolts or 0.025 volts. So in approximate circuit analysis, we use this value of thermal voltage at room temperature. We can also express this diode equation in logarithmic form. We know that common log means base 10 log. It tells you what power you must raise 10 to obtain the number x, that is n is equal to 10 raised to the power x. Similarly, second is natural log, which means base e log. It tells you what power you must raise e to obtain the number x, that is n is equal to e raised to the power x. So, which log you are going to apply here? You are going to apply natural log here because you have this e in your equation. So, after applying natural log on both sides of this equation, you will get ln I is equal to ln Is e raised to the power v divided by n Vt minus 1, or we can also write this equation as Is ln e raised to the power V divided by NVT minus IS ln 1. Here this ln is cancelling this E, and we know that the natural log of 1 is 0, so this whole term becomes 0. Now you'll get ln I is equal to IS V divided by NVT. Now by rearranging we get V is equal to NVT ln I divided by IS. So this is another way of writing diode equation in terms of V. Look at this example. If you have N is equal to 1 and voltage of silicon made diode is 0.7 volts and you have to find current. So how you are going to find this current? You will use diode equation. I is equal to IS E V divided by NVT minus 1. Now what is IS? Take this IS 10 raised to the power minus 15. It is also fixed in most cases. Now we know what is V, we know what is N, and we know what is VT. VT is 0.025 volt. So after putting all these values in this equation, you will get I is equal to 1.44 into 10 raised to the power minus 3 amperes, or I is equal to 1.44 milliamperes. So this is how you are going to find current using diode equation. Now we will understand derivation for increasing current when voltage is increased in forward bias region. Now, for suppose current I1 is corresponding to diode voltage V1 and it is given by the equation I1 is equal to IS e raised to the power V1 divided by NVT, and we call this equation equation 1. Similarly, current I2 is corresponding to diode voltage V2, which is given by the equation I2 is equal to IS e raised to the power V2 divided by NVT, and this is equation 2. Now if we divide equation 2 by equation 1, we'll get I2 divided by I1 is equal to IS e V2 divided by NVT divided by IS e V1 divided by NVT. Now this IS is cancelling this IS, and if we move this E in numerator, then we know that its power will become negative, and if bases are same, then we add their powers. So this equation now becomes E V2 minus V1 divided by NVT. Now again we have E in our equation, so we will take natural log on both sides. So after taking log on both sides, we will get ln I2 divided by I1 is equal to V2 minus V1 divided by NVT, which can be rewritten as V2 minus V1 is equal to NVT ln I2 divided by I1. Now, for converting this natural log into base 10 log, we multiply base 10 log by a conversion factor 2.3 It means ln is equal to log 10 2.3. So now this equation can be rewritten as V2 minus V1 is equal to 2.3 n Vt log I2 divided by I1. So this is your derivation for increasing current when voltage is increased in forward bias region. For decayed change in current, I2 is equal to 10 I1. We know that V2 minus V1 is equal to 2.3 NVT log I2 divided by I1. Now we'll put this value of I2 from this equation in this equation and we'll get V2 minus V1 is equal to 2.3 NVT log 10 I1 divided by I1. This I1 is cancelling this I1 and we know that log 10 is equal to 1. So we'll get V2 minus V1 is equal to 2.3 NVT. Okay. Now if N is 1 and we know that Vt is 0.025 volts, then V2 minus V1 is equal to 2.3 multiplied by 1 multiplied by 0.025. It will give us 0.0575 volts or 57.5 millivolts. Okay, so this is how you are going to solve different problems using this equation. Now here is your class task. Using diode current equation, find value of saturation current at both n is equal to 1 and 2 when forward voltage is 0.7 volts and diode current is 1 milliampere. Take thermal voltage 25 millivolts. Okay, take 3 minutes to complete this task. Now we will understand modeling of diode in forward characteristics. For analysis of circuits, diode is represented with a model. It is done to find function of diode and unknown quantities like diode voltage and diode current. There are many ways to model the diode in forward characteristics. Here we will discuss simplified diode models that are better suited for use in circuit analysis and design of diode circuits. First, we will consider exponential diode model. This model is the most accurate description of the diode operation in the forward region, but it is most difficult to employ in circuit analysis. Why? Because of its nonlinear nature. Now, let's analyze this circuit using the exponential diode model. Assume that this VDD is greater than 0.5 volts or so. Now here this 0.5 volts is cut-in voltage. Now what is this cut-in voltage? If you remember that in forward region the curve is something like this. This is current and this is voltage. So the cut-in voltage is the voltage after which the diode current rapidly increases. It means this is the point after which the current is rapidly increasing. So this is what we call cut-in or knee voltage. In silicon diodes, it is 0.7 volts. Okay. Now here we assume that this diode current, it is much greater than saturation current. It means it is another assumption. We know that the diode current is given by the equation which is shown here, where this Vd is the voltage across diode. Ideally, this Vd is 0, but in practical cases, it is 0.3 volts for germanium and 0.7 volts for silicon diodes. Now, this ID is current across diode. Now, the other equation that governs circuit operation, it can be obtained by using Kirchhoff voltage law. We know that this is positive terminal of the battery, this is negative terminal. So this terminal of R is positive, this is negative, and this terminal of diode is positive and this is negative. Now, how we are going to make KVL equation? We'll start from this point, means minus VDD plus, I'm calling voltage across this resistor VR. So plus VR plus Vd is equal to 0. Now we know that this VR, it can be written as I dr, because we know that V is equal to IR. Here this I is ID and R is R, plus Vd is equal to 0. Now if you rearrange this equation, you will get ID is equal to VDD minus VD divided by R. So this is another equation of diode current that you are getting from KVL. Now, we know that this is first diode current equation. Here, this diode parameter Is is known. This N is 1 for diode. This Vt is constant. Now, look at this another current equation for diode. Here, the values of this VDD and R are also known. So, in these two equations, there are two unknown quantities which are Vd and Id, that is diode current and diode voltage. So, there are two alternative ways for obtaining the solution. First is graphical analysis and second is iterative analysis. First we will understand graphical analysis. Graphical analysis is performed by plotting the relationships of previous two equations of diode current on the IV plane. Now this is the IV plane where the variable of x is Vd and the variable of y is Id. It means diode voltage is on x-axis and diode current is on y-axis. We know that first equation of diode current is Id is equal to Is e raised to the power v divided by n Vt. Now how you are going to draw this relation on this IV plane? It is drawn something like this. Here this curve is representing this exponential diode equation. Now we know that the second equation of diode current is ID is equal to VDD minus VD upon R. If we break this equation, we get ID is equal to VDD divided by R minus VD divided by R, or we can rearrange this equation like minus VD divided by R plus VDD divided by R. Now we know what is a slope. The slope of a line describes its steepness or incline. Its formula is y is equal to mx plus c, where this y represent variable on y-axis, this x is representing variable on x-axis, and this m is slope. Now if we compare this formula of slope with this equation of diode current, then we can write it like y is equal to ID, x is equal to VD, m is equal to minus 1 upon R, and c is VDD divided by R. So how you are going to draw this relationship that we obtained in this second equation of diode current on this IV plane? We draw this relation something like this. It means it is a straight line which is representing the diode current equation which is obtained from KVL. This straight line is known as load line. It is a slope, and the direction of this slope is downward from left to right. It means when voltage increases, current decreases. As you can see, this load line is intersecting this curve at this point. We call this point Q. Now, this point Q is representing the operating point of the circuit. The coordinates of this point Q, they give us the values of ID and VD. It means when we draw line from this point Q on x-axis, we get the value of VD, and when we draw a line from this point Q on y-axis, we get the value of ID. Okay, this is slope, which is minus 1 upon R. Okay, now look at x-axis. At x-axis, we know that ID is equal to 0. Now, if we put ID is equal to 0 in this equation, what we'll get? We'll get VD is equal to VDD. Okay, so at this point, we will write VDD. Now, note that this VDD, it can never be 0. Why? Because it is a source. Okay, now look at y-axis. At y-axis, VD is 0. So when we put this VD 0 in this equation, we'll get ID is equal to VDD divided by R. So at this point, we have VDD divided by R. Okay. So this is how we will obtain values of diode voltage and diode current through graphical analysis. Now, look at this example. We know that ID is equal to VDD minus VD upon R. If R is 5 ohms and VDD is 5 volts, then what is the value of diode current in case of ideal diodes and in case of practical diodes? We know that in ideal diodes, VD is equal to 0, therefore ID will be 5 minus 0 divided by 5, which will give us 1 amperes, and we have Vd is equal to 0.7 volts in case of silicon diodes, and this Vd is 0.3 volts in case of germanium diodes. So here diode current will be 5 minus 0.7 divided by 5, which is equal to 0.86 amperes, and here ID will be 5 minus 0.3 divided by 5, which will give us 0.94 amperes. So this is how you are going to find diode current using KVL equation. Now we will understand iterative analysis. The previous equations can be solved using a simple iterative procedure, which is illustrated in this example. Determine the current ID and the diode voltage Vd for the circuit where VDD is 5 volts and R is 1 kilo ohms. Here we assume that the diode has a current of 1 milliamperes and it has a voltage of 0.7 volts. Now, to begin the iteration, we assume that Vd is equal to V1 is equal to 0.7 volts and I1 is 1 milliampere. It means the values that you are given, they are V1 and I1. Okay. Now we will find ID, which is diode current. How you are going to find ID? You will use KVL equation, which is ID is equal to VDD minus VD divided by R. Here VDD is 5 minus 0.7 divided by 1 kilo ohm. So you will get 4.3 milliamperes. Now how you are going to find Vd? This can be done by employing the equation that we have derived earlier. This equation is V2 minus V1 is equal to 2.3 NVT log I2 divided by I1, or V2 is equal to V1 plus 2.3 NVT log I2 divided by I1. Now here this V2 is Vd. Now we know that the value of N is 1. We know that the value of Vt is 0.025. Now here what is I2? This value of ID that you have derived, it is I2, and you know I1 is 1 milliamperes. So after solving this equation and after putting all the values, you will get the value of V2, which is what? Which is 0.736 volts. Okay. So this is the result of first iteration, where the value of ID is 4.3 milliamperes and the value of VD is 0.736 volts. Okay. Now we will start our second iteration. It will proceed in a similar manner. Now for second iteration, the previously obtained values of V2 and I2, they will become V1 and I1 for second iteration. So the value of V1 in this iteration will be 0.736 and the value of I1 is 4.3 milliamperes. Okay, now first we will find ID or I2 by using KVL equation. ID is equal to VDD minus VD divided by R. Now in this case, VD is 0.736 and we know that R is 1 kilo ohms. So we will get 4.264 milliamperes. Now we will find VD or V2 by using formula. V2 is equals to V1 plus 2.3 NVT log I2 divided by I1. We know what is V1. V1 is 0.736. We know what is N. N is 1. We know that VT is 0.025. We know that I2 is 4.264 and I1 is 4.3 milli. So after solving this, you will get V2 is equal to 0.735 volts. Okay, so the results of second iteration are ID is equal to 4.264 milliampere and VD is equal to 0.735 volts. Now we will start our third iteration. The third iteration proceeds in a similar way. It means the values of V2 and I2 that are obtained in second iteration, they will become V1 and I1 in this third iteration. So here V1 is 0.735 volts and I1 is 4.264 milliamperes. This V1 is also VD. So first we will find ID, which is also known as I2 by using KVL. So ID is equal to VDD minus VD divided by R, that is 5 minus 0.735 divided by 1 kilo is equal to 4.265 milliamperes. Now we will find V2 or VD using this equation. V2 is equal to V1 plus 2.3 NVT log I2 divided by I1. We know that N is 1, VT is 0.025, I2 is 4.265 and I1 is 4.264 milli. Now V1 is 0.735. Now after solving this equation, you will get V2 is equal to 0.735 volts. Okay, so the results of third iteration are ID is equal to 4.265 milliamperes and VD is 0.735 volts. Now note that the values of ID and VD that you have obtained in this third iteration, they are almost similar to the values obtained in second iteration. As you can see, this VD is exactly the same as the value of VD you obtained in second iteration. Similarly, the value of ID here in third iteration is 4.265, whereas the value of current obtained in second iteration is 4.264. It means they are almost similar. So no further iterations are necessary, and the final values of ID and VD will be 4.265 milliamperes and 0.735 volts. So this is how you are going to find unknown quantities, that is diode voltage and diode current, using iterative analysis. That's all for today. What are the key takeaways of this lecture? In this lecture, you studied about current equation of diode. Here you also understood exponential diode model, which uses two alternative ways for obtaining values of unknown quantities like diode voltage and diode current. First way is graphical analysis and second way is iterative analysis.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.